I just allowed you to record the lecture. You should be able to.
Thank you.
Sure. And for you, when it doesn't give me the option, I don't know
I
why.
think I got it.
Okay, good. I'm gonna start the lecture in 2 minutes because there is only 19 participants. So I'm gonna start in 2 minutes. All of you guys allowed to record? Okay.
Yeah, I'm able to record.
Okay, good. I am going to record the lecture myself and share my screen with you guys. Let's go to all right. Yeah. We are in chapter 4, applying first law to a closed system. We were up to, we talked about the specific heat, CP and CV. Did we talk about the specific heat, DP and CV? Yes or no? I think we did.
I think it
Can I
was
get
the
a
last things.
Yeah, we went
what's
over
that?
these.
I don't.
Okay, good. We went over. All right. Yeah. We're up to this example, I think. Please have a piece of paper. We want to review a couple of examples. Air is contained in variable load piston cylinder device, which is equipped with paddle wheel. Initially, air is at 400 kilopascal and 17 degree centigrade. That's the initial condition, P1 and T1. The paddle wheel is turned by an external electric motor until 75 kilojoule per kilogram of work has been transferred to air. That lowercase w because it's work per unit of mass. During this process, heat is transferred to maintain a constant temperature. So also heat is being transferred and temperature remains constant while the gas volume triples. So V2 is 3 times V1. We want to calculate the required amount of heat transfer in kilojoule per kilogram. Let's go to the next page and see. Here is variable load piston cylinder. So pressure can change because it's variable load. The initial condition is given. P1 is 400 kilopascal. T1 is 17 degree centigrade. You add 273, that makes it 290 degree Kelvin. Lowercase w, it should be lowercase w. It's 75 kilojoule per kilogram. That is work per unit of mass. And also heat is being transferred, which is to be determined. Heat is being transferred until the volume is triple times initial volume. So V2 is 3 times V1. Meanwhile, the temperature during this process going from a state 1 to a state 2 we maintain a constant temperature. What you should do, you should apply the first law or energy balance equation to this system, which is piston cylinder and the fluid, which is air inside it. By the way, there is also paddle wheel, right? That's the work of paddle wheel. So you should start with energy balance equation or the first law and apply it to the system. And, um, substitute for each term. It's a closed system. There is no mass transfer into or out of the system. So the only way energy can be transferred into or out of the system is through heat and work. And it should also work on the right side of the equation. Change of energy of the system manifests itself in changing kinetic energy, changing potential energy, and changing internal energy. And the system, it's just that it is a stationary. So there is no change in kinetic or potential energy. So the right side will be limited to change of internal energy. I'm going to stop on the first page. So you have the problem. I'm going to give you, let's say, 5 minutes or so. And then I'm going to ask you questions. I need volunteer. So I'm right here, but I'm going to mute myself. And your time is done. Do your best and use this time like it is, exam or something. You have 1 minute left. 1 minute left. Okay, anyone wants to, because I'm gonna put it in steps. Anyone wants to explain what happens to the right side of energy balance equation? Your system is piston cylinder and the air inside it. You apply the first law because you are looking for heat transfer to it. So you say, okay, I'm gonna apply first law or energy balance equation to this system. So E in minus E out is delta E of the system. E means the total energy transfer into piston cylinder. E out is the total energy transfer out of the system, and that is delta E of the system. Delta E of the system is changing kinetic energy of the system, changing potential energy of the system, and change in internal energy of the system. So delta KE, delta PE, and delta U. What do you say about delta PE and delta KE and delta U? Anyone?
I'm sorry, Professor, are you writing this down?
No, I'm not going to the next page because I have solution on the next page. I just want to ask you guys,
Gotcha.
what do you think? Yeah. So anyone can explain what happens to the right side of energy balance equation, delta KE, delta P, and delta U? Any volunteer? What do you say about delta KE changing kinetic energy of the system? The system is piston cylinder.
There's no kinetic energy? Is that what you mean?
There is no change in kinetic energy, right? And
Uh-huh.
why is that? Why is that? Because,
There's nothing moving, it's static.
yeah, exactly. The system is stationary. And what do you say about changing potential energy?
It's still static, so there's no potential energy.
Exactly. Your name?
Tom?
Thank you,
Thomas.
Tom. Yes.
Mhm.
There is no change in kinetic energy and there is no change in potential energy because the system is stationary. There is no change in velocity or elevation of the system. We are talking about piston cylinder, absolutely. How about the change? So the change in energy of the system will be narrowed down to change in internal energy of the system, right? What do you say about changing internal energy of the system?
It went up by 75?
That's a work. I'm talking about the right side of energy equation. See, let's go to the next page.
It's the heat that we added.
What's that?
It's the heat that we added, which is related to U2 and U1.
The heat is in the left side. See, we have E in minus E out is delta E. We are not talking about the left side yet. We are focusing on the right side. See, change in energy of the system, changing, energy of that, piston cylinder and the fluid basically inside it is changing kinetic energy and changing potential energy and changing internal energy. As Tom explained, these two are zero because the elevation of the system doesn't change and the velocity of the system doesn't change, the system is stationary. These two terms goes to zero. These are part of change of energy of the system, changing kinetic energy and changing potential energy. And change in internal energy. So change in energy of the system will be limited to change in internal energy. And we learned that for air, it is mCV delta T, right? Change in internal energy is M for gases, mCV for gases. That's capital U. Capital U means for the whole system. So it's mCV delta T, T2 minus T1. If it was lowercase u, it was CV delta T, which is CV T2 minus T1. Anyhow, going from a state 1 to a state 2, temperature remains constant. So T2 and T1 are equal. So there will be no change in internal energy. So that goes to 0 too. So basically, the right side of this equation is 0. So the energy balance equation will be limited to, and it's a closed system, piston cylinder. E in and E out in general is Q in, part of E in, Q out, part of E out, W in, part of E in, W out, part of E out. And also, if the system was open, which is not the case here, if the system is open and there is inflow and outflow of mass, there is inflow and outflow of energy. And inflow of energy through mass, if mass flow rate is m dot, that's going to be m dot times energy per unit of mass. The term the Prandtl test as energy per unit of mass, which is kinetic energy per unit of mass, V squared by 2. Potential energy per unit of mass, which is Gz. And enthalpy per unit of mass, which is H. And enthalpy itself is U plus P over R. U is internal energy per unit of mass, and P over rho is called flow work or flow energy. That is the energy that 1 unit of mass of flowing fluid needs to flow. Energy that 1 unit of mass of fluid needs to flow. But in this case, we don't have to be worried about m dot part, energy transferred by mass, because the system is closed. So the energy transfer into out of the system will be limited to heat and work. And we have Q in and we have Q out. Q in minus Q out is Q net in. And we have W in and we have W out. That's W net in. We can also write it this way. Q in minus Q out, pack Q's together and pack W's together, plus W in minus W out is 0. That's energy balance equation, the first law. We just apply the first law to this system. There is heat transfer into the system. Let it be. That needs to be determined. There is no mentioning of losing heat or heat transfer out of the system. So 0. There is work in, right? Work transfer into the system, which is by paddle wheel. That work will be added to the system. That shaft work will be added to the system. So that is part of W in. What do you say about W out? Work transfer out of the system. If there is expansion, that work is out. Anyhow, we do know that there is boundary work involved. And we need to calculate the boundary work. That's part of work, right? And because the problem implies that volume at a state 2 is triple times the volume at a state 1. So we do know that volume increased. And volume increased, it means there is expansion. It means there is boundary work involved. And because that boundary work, because the boundary of the system changed, because that boundary work is expansion, that work is out of the system. Expansion is boundary work, which is out of the system. I discussed that last time. Compression is the boundary work that will be added to the system. So compression is part of W in, but expansion is part of W out. So there is W out, which is basically boundary work. The volume triple. We need to calculate the boundary work. So it's WB from a state 1 to a state 2. We know the formula. It's integral of PdV. And we need, in order to take this integral, we need to write P, pressure, as a function of V, right? It's ideal gas. So there is a relationship between P and V. We know PV is MRT, right? MRT. And going from a state 1 to a state 2, MRT is constant because going from a state 1 to a state 2 during this expansion, it's the same mass. Mass doesn't increase or decrease, conservation of mass. And R is the same. R is a specific gas constant as long as it is the same gas, which is the case. R is the same, specific gas constant. And going from a state 1 to a state 2, temperature remains the same. So MRT remains constant. So basically P is that constant divided by volume, or MRT divided by volume. So you write P as a function of MRT over volume, or a constant, which is MRT over volume. We name this MRT, T for constant. So it's T over volume. So you can take it out, take T out. And integral of dV over V is ln of V. We apply upper bound and lower bound. It's ln of V2 minus ln of V1. Based on what we have learned in algebra, ln of A minus ln of B is ln of A over B. So it's going to be the ln of V2 over V1. That's the, as we know, it's MRT. For the simplicity, we just substituted T. So now we are going to write it down and write it in terms of MRT. So it's MRT here. And it's ln of V2 over V1. V2 is 3 times V1. So it's ln of 3. So it's MRT ln of 3. All right. So MRT ln of V2 over V1. We are going to work parametrically, and at the end, we are going to, substitute and plugins. Here, I mentioned that there is other way to calculate PV. You can write everything in terms of nu. So we know volume over a specific volume is M, mass. So a specific volume is volume over M. So you just substitute dV and write it in terms of d nu, and then write pressure in terms of nu and take this integral. We get the same result. I'm gonna skip this part. You can review this when you review this slideshow. So when you plug everything into this equation, let's go back, energy balance equation. You have MRT ln of V2 over V1 for W, this part. You have, let's do it this way. Look, because we have Q, we are looking for Q, and we have, let's go back one step before. So we got to this point, right? Now we have W out, and we have W in. But we have W in, which is work of this shaft, right? This sphere, per unit of mass. It's 75 kilojoule per unit of mass. It's not capital W, so okay. So what we do, because we don't have the mass, we are going to divide both sides of this equation by M, the mass of this air. When you do that, this becomes capital W general, but when you divide it by M, it becomes lowercase w, which is work per unit of mass. That's 75. And when you divide this, which is boundary work, WB by M, because boundary work, as you calculated, you got to this point, it's MRT ln of V2 over V1. You substitute for this and divide it by M. You get RT ln of V2 over V1 for this term, right? And then Q becomes lowercase q, because when you divide capital Q by M, capital Q is the total heat transfer to the air. We divide it by mass of air. It becomes lowercase q, which means a heat transfer per unit of mass. So that's equation 1, which is first law. right? When this is first status, this is equation number one. We just divide both sides by m and substitute whatever we had. That is for W in, lowercase w, 75 kilojoule per kilogram, which is work of, paddle wheel. That is for W out, which is basically the boundary work, WB. When you divide it by M, RT ln of, 3, right? And that is to be determined, but it's gonna be lowercase q when you divide both sides by M. That is the transfer to the air per unit of mass. Then you just substitute for R, which is for air, an SI system that is 275 joule per kilogram, for T, which is remains constant between 1 and 2. You have to convert it in absolute temperature. And here is ln of 3. You can plug it into calculator. Here is 35. So the only unknown here is Q. And when you plug everything in, the numbers, you get 16.4 kilojoule per kilogram. That's the heat transfer per unit of mass of air. And that's all I can Q. Any
Professor?
question?
Yeah,
Yes.
I have a question. I don't quite understand how the M mass for W out gets canceled out.
See, you don't have M, right? You want to get rid of M. So up to this point, you have, that's the same equation, energy balance equation. You have Q in, right? There is a Q out. That's heat gain that you are looking for. That's the heat that you supply and you are looking for. The value of that. That's the boundary work, W out. Here is the boundary work between 1 and 2 MRT ln of V2 over V1. So that's for this parameter. And here you had capital W, which is capital W in. That is work into the system by the paddle wheel. But W, capital W, is M lowercase w. This means work by paddle wheel per unit of mass transfer to the air per unit of mass times M, that makes capital W. Now, we're going to divide both sides of this equation by M. When you divide this term, M cancel out. So we are going to have work of paddle wheel per unit of mass, which is 75 kilojoule per kilogram. And that becomes, because this guy is equal to this expression, and when you divide by M, it becomes RT ln of 3, volume at state 2, it's 3 times volume at state 1. And then that becomes lowercase q, which is heat transfer per unit of mass. Let's go to the next page. Here we have Q in plus 75 minus RT ln of 3. You just plug in for R for air, specific gas constant, and the temperature, which is the constant temperature between state 1 and state 2, T1 and T2 are equal. 75, the paddle will work per unit of mass, and here is lowercase q that we are looking for. And you get 16.4 kilojoule per kilogram. All right? Is it clear now? I need a confirmation.
Yeah, that makes sense, Professor. Thank you.
Okay, of course. Let's do another example. A 10 feet cubic tank contains oxygen, initially at 14.7 psi. Psi means pound per square inch. That's the initial pressure, P1. And 80 degrees Fahrenheit, that's the initial temperature, T1. A paddle wheel within the tank is rotated until the pressure inside rises to 20 psi, 20 pounds per square inch. During this process, the heat is being transferred, and that heat is 20 BTU. Oh, it loses that much heat. 20 BTU of heat is lost to surrounding. That's the heat loss. We want to determine paddle wheel work done. We are looking for work of paddle wheel. So in previous case, previous example, we had the work, we were looking for heat transfer. In this case, we have the heat transfer, we are looking for work. neglect the energy stored in paddle mill. So I give you 5 minutes or so to construct the solution, then like previous case, I'm going to answer your questions. All right. I'm right here. If you have any question, you can ask me, but I want to mute myself. Okay, anyone? Let's start with energy balance equation. You should apply energy balance equation to this system. Anyone can explain the first step?
I could try, and by that I mean succeed.
Yes, please, your name?
Sargis?
Okay, yes, please. Please go ahead.
Cool. So as we found out before, energy in minus energy out has to equal, you know, that's the total energy, the change in energy. And
Mhm.
just like last problem, there's no kinetic energy or potential energy being like lost or gained. And since the
Mhm.
temperature stays the same within the entire thing, our change in U is also 0. And so that means the entire right side is equal to 0, which is very convenient. And so now we have the equation left of Q net in plus Q net out, W net in equal to 0. If we broke those down into Q in minus Q out plus W in minus W out equals 0. I
Mhm.
believe we don't have any Q going in, or there's no heat going in, so that would be 0, and that goes away from our equation. And so we have
Mhm.
negative 20 BTU plus the work that we put in.
Mhm. Okay, thank you.
Minus, okay.
Yeah, thank you. So, look, we apply energy balance equation first law, as you just explained, your friend just explained, A in minus E out, delta E of the system, right? Let's work on change in energy of the system. That is change of kinetic energy and change in potential energy and change in internal energy. The system is stationary, right? So there will be no change in kinetic energy or potential energy because there is no change in velocity, of course, and elevation of the system. How about delta U? Let's keep delta U. Look, there is no mentioning of temperature. The only thing, because you said delta U is 0, there is no mentioning of temperature being constant. In previous case, temperature was constant going from a state 1 to a state 2, but not in this case. So let's just keep delta U for now. And list all the known and unknown. We know P1 is 14.7 psi pound per square inch. T1 is 80 degree Fahrenheit. Volume at state 1 is 10 feet cubic, as mentioned. P2 is 20 psi. And volume doesn't change. The rigid tank. So another piece of information we have about SA2 is V2 is the same as V1, and it is still 10 feet cubic, which is the volume of the tank, not like case SA1. We are looking for W in working, right? In previous example, we had working the system by paddle wheel, but in this case, it's unknown. Work out of the system W out is 0. There is no mentioning of losing it, and there is no body work involved. And Q in, there is no mentioning of supply heat, so Q in is 0. Q out is 20 BTU, that's a heat loss that is given, right? So we listed all the values and parameters that we have. So here is the energy balance equation of the first supply to this system, to this tank, and the fluid inside it. W in, let it be. It needs to be determined. Q in, there, as I just mentioned. That is E in. By the way, the system is closed, so you don't have to be worried about energy transferred by mass because mass cannot cross the boundary of the system. And these two terms that you see, that is for E out. W out 0, no mention of work out of the system, no boundary work, nothing. And Q out, which is the heat loss, 20 BTU. There is no heat gain, that is 0. And this is let it be because it needs to be determined. On the right side is delta U, which we know it's mCV delta T, mCV delta T, which is T2 minus T1. We have T1, we don't have T2. We're looking for W in. So let's simplify this. It's 0, 0, take this to the other side with plus sign. Here we are. And we have the value. We can substitute later on. And we just add Q out to this term. So basically W in, which we are looking for after simplifying it. Is MCV T2 minus T1 plus Q out. Q out we have, T1 we have, CV we can get it from the table based on the average temperature, or it's given. In this case, I think it's given. Yes, it's given. Yeah, CV is given. So we have the value. It's given as 0.6 n. BTU per pound mass per ranking. That is given. So we have this. We need to calculate M and T2 and plug in, and we are done. Let's see how we can do that. How we can get T2? Let's go back. How we can calculate T2? Because I have T1. I need to calculate T2. CV is given. I need to calculate M. I have QR. So two parameters I need to plug in and I need to calculate T2 and M. And then we are done. How we can calculate T2? Anyone? It's ideal gas. The substance is ideal gas. How we can calculate T2 having T1? I am waiting.
You could do T2 equals P2 T1 over P1.
You can use ideal gas or your name.
Ardisher.
Yes, see. We can use ideal gas law, right? We know P1 V1 over T1 is equal to P2 V2 over T2. That's ideal gas law. And we know it's rigid tank, so V1 is equal to V2, so that cancel out. So T1 over T1 is equal to P2 over T2, and I'm looking for T2. The T2 is P2 over P1, T1, and I have T1. Remember, P should be expressed in absolute temperature, pressure, and T absolute temperature. So it is Fahrenheit. You have to add 460 to convert it to Rankine. But for this, you don't have to convert to absolute pressure because it's ratio. We need the ratio. The 220, which is P2 over 14.7, which is P1. So just plug in and you can calculate T2 at 735 Rankine. And we also need to calculate M. Again, use ideal gas law. We know PV is MRT and we need M. So M is PV over RT, which can be P1, V1 over RT1. We have T1, that's absolute temperature, right? And, you have R, and T1 is 540 Rankine. And you have R, you can get it from the table for air. The unit should be consistent, and we have P1, right? Which is 14.7 psi. And you have V1, which is 10 feet cubic. You just plug everything in, and you get M as 0.812 pound mass. And then you plug everything into the equation, energy balance equation on the first law. And when you plug in, you get, sorry, that shouldn't have dot, please fix it. W in, or work transfer into the system, it's 45.3 BTU. All right. Here I mentioned, I don't know why I did that, but I mentioned that enthalpy, lowercase h, which is enthalpy per unit of mass. By definition, the way we define enthalpy is U internal energy per unit of mass, that is lowercase, it means per unit of mass, plus P nu. P is pressure, and nu is specific volume, which is 1 over R. So it's U plus P over R, or P nu. If you multiply both sides by M, you have capital H, which is enthalpy for the whole mass M. You have capital U, and you have P, and you have, instead of a specific volume, we're going to have V, because we'll multiply this term by M. It's like P M over R, and over M over R is volume. By the way, this term, fellow work or fellow energy, which we discussed before, that the energy that 1 unit of mass of fluid needs to flow, nothing is for free. Is there any question before I proceed? No questions whatsoever? All right. We are done with chapter 4. Now we can
Heather,
move
I do have a
to
question.
chapter. Yes, please.
I kind of don't understand the conversion of units you did. So like for example, to find the temperature, you said it was
Mhm.
735 R. I don't know what that means.
Ranking.
Ranking.
You add 460, yeah, because you are working in English system. If for SI, you go for absolute temperature because T should be absolute temperature. If it was SI system, you should go Kelvin. So you should add 273 too.
Oh,
That's
okay.
it.
So if we're
Right.
in
You
if we're in
get, yeah,
Fahrenheit.
exactly.
Okay, so
Exactly 460.
okay.
You add 460 to Fahrenheit to convert it to ranking. Exactly. So let's, for now, let's stop sharing. I'm gonna find the chapter 5 and we're gonna go to chapter 5. We are done with chapter 4. By the way, we set the date for, midterm, right? And what is the date?
Next Thursday. Sorry, next Wednesday.
Which is next Wednesday, which is April
The 6th.
next, April 6th, right? All right. So it's April 6th. We are gonna have the midterm.
It's
All
on
right,
chapter
which,
1, 2, and 3, right, Professor?
yes, chapter 1, 2, and 3.
Thank you.
Yeah, of course.
Professor, are you gonna
All
still
right,
have those
let
Zoom
me,
lectures? Those extra credit Zoom
what's
lectures?
that?
Are you still gonna have the extra credit tutoring or whatever you said you're gonna do?
See, in April, we're gonna have a couple of Zoom lectures, right? In addition to in class. Next week, we are gonna have in class. We continue in class, but as I explained, we're gonna have a couple of Zoom sessions in addition to those, and I'm gonna offer extra credit for those. Yeah, I'm gonna announce the date. All right. Yeah. So let me go to chapter 5. Give me a sec. Okay. All right, chapter 5. Let me copy this. All right, let me share my screen with you guys. And chapter 5, session 1. See, in chapter 5, it's audio recorded as well. We want to apply the first law to open system. To open systems like, let's say a section of pipe, nozzle, diffuser, air duct, for example, a heat exchanger, mixing chamber, throttling valves. All of those open systems when mass can cross the boundary of the system. Previously, chapter 4, we were working with closed system like piston cylinder when mass cannot cross the boundary of the system. So we are going to talk about, I listed the engineering devices that we are going to work with and apply the first law of thermodynamic or energy balance equation to like pipe and duct flow, heat exchanger, turbine and compressor, pump, nozzle and diffuser, mixing chambers, and so on. So again, we start with conservation of mass. We talked about conservation of mass before. It's very simple. Mass cannot be created or destroyed. When you apply it to a system, we name it continuity equation. So it is mass balance equation, which is continuity equation, like energy balance equation. when we name, like, a first law of thermodynamics and energy mass balance equation. It's called continuity equation. So when the system is open, this is your system. Think of it like a black box. It can be anything, like airtight, like mixing chambers, like a section of pipe. There is inflow of mass into the system. There is outflow of mass out of the system. And, if these two don't balance, the difference goes to change of mass of the system. So M in minus M out is delta M of the system. For example, if there is 10 units of mass going in, and there is 7 units of outflow of mass, 10 minus 7 is 3. That is increase of mass inside this control volume or system, whatever the system is. You can also write it in terms of rate. So M dot in is mass flow rate into the system. That is mass per unit of time. And M dot out is outflow of mass, rate of outflow of mass from the system. So M dot in minus M dot out is rate of change of mass in the system, right? And here I explain how we can calculate rate of change of mass. It's kind of out of the scope of this course. We do that in fluid mechanics, ME390. The way you should calculate rate of change of mass. First, we need to calculate mass inside the system, because density doesn't have to be uniform within the system. For example, it can be air, and the system can be compressor, for example. So density at different point, density of mass at different point is different. So it's not like density is the same, uniformly distributed, and then just multiply density by the volume and say, okay, here is the mass. No. You have to divide the whole system to differential volume and calculate differential mass for each differential volume, which is rho d volume. Rho at this point times the volume. That's differential mass. And then you take integral over the whole system, over the whole control volume, and that gives you mass of the system. And here is rate of change of mass of the system. It's d of this integral, because this is mass of the system, d of mass of the system dt. It's the rate of change of mass of system. But it's kind of out of the scope. We want to see how to calculate mass flow rate and volume flow rate. I think previously I talked about that, but let's have this review. If this is a section of pipe, for example, that is your system. The system is open. Chapter 5, the system is open. So there is inflow of mass, there is outflow of mass. If velocity at the inlet is V in, at the outlet is V out. Mass flow rate, which is mass crossing each section of this pipe, is rho VA, because VA is volume flow rate, velocity of the fluid multiplied by area. For example, cross-sectional area of this pipe, VA, is volume leaving or crossing this area per unit of time. And when you multiply by rho VA is mass flow rate, mass crossing each section of this pipe, for example. V dot is volume flow rate, volume crossing each section of this pipe, which is VA. So basically mass flow rate is density times volume flow rate. The very same way we say mass is density times volume. Mass flow rate is density times volume flow rate, and volume flow rate is VA. We assume that velocity is uniformly distributed over this section. See? If it's not uniform, you should take average and use average in this formula. So it's going to be V bar. We consider the average velocity. By the way, Here I mentioned we use V, which is perpendicular to the area. In this case, velocity is perpendicular to the area. If it's not, I put it under a note. See, in the formula, when you calculate volume flow rate, this is for volume, that is for volume flow rate, which is VA. Velocity, that is velocity. Velocity of the fluid times A. I'm referring to this. Velocity of the fluid times A, that is volume flow rate. And mass flow rate is the density times volume flow rate, that makes it rho VA. This velocity V, the component of velocity which is perpendicular to the area. See, velocity is perpendicular to the area. Oh, it should be V, not P. Please make a little note and fix it. V. If V is not perpendicular to the area, like this one, you should resolve it into two components, the tangent component and the normal component. You don't care about tangent component V2, which is V sine of theta, because that doesn't take any fluid in and out. You only consider V1, which is V cosine theta, the normal component. And when you want to calculate volume flow rate, you should use the normal component, which is V1. So it's not VA, it's V1A, because V has to be perpendicular to A, and only V1 is perpendicular to A, not the whole V. So it's V1A, which is V cosine theta A. So M dot would be rho V1A, which is rho V cosine theta A. Under note 2, I explained that we already assumed that velocity is uniformly distributed across the section like this one. And we say, okay, it's U or V times A. But if it's not uniformly distributed, like width gets below in pipe, fully developed width gets below in pipe, here is how velocity looks like. You learn about the stuff in fluid mechanics. In that case, you should consider the average velocity, which for, which gets below, fully developed which gets below in circular pipe. The average velocity, we can prove that. I do in fluid mechanics. Half of velocity at the center, VT, or center velocity, which is the maximum velocity. So it's half of the maximum velocity. The volume flow rate, which is VA, in that case, which velocity is not uniformly distributed across the section, it's average velocity times A. That makes M dot rho V bar A, V bar for average velocity. Please also review these two examples within chapter 5. Example 1 and 2, the solution is within chapter 5. Now, I want to explain that if, we are dealing with steady condition, steady, flow, then, steady means nothing changes inside the control volume. Nothing changes inside the system. It means that when you, let's go back. Here. When you say M dot in minus M dot out is rate of change of mass inside the system, that's a conservation of mass. M dot in minus M dot out is these two don't balance. The difference is rate of change of mass inside the control volume, or M dot, delta M dot of system, change of, delta M of the system, change of mass inside the system, right? So if the system is steady, it means mass inside the system cannot increase and it cannot decrease. Nothing can change inside the system. Nothing. For example, if it's a section of pipe, nothing can change inside the section of pipe. Energy cannot increase or decrease. Mass cannot increase or decrease. So it means the right side of this equation is 0. That makes M dot in being equal to M dot out. So mass flow rate into the system should balance mass flow rate out of the system. These two should be equal. So in 1 unit of time, these two should balance. If 10 units coming in, 10 units has to leave, because if these two are not equal, then the difference according to conservation of mass cannot disappear or created. So the difference goes toward increase or decrease of mass inside the system, which contradicts with being under a steady condition, because a steady means nothing can change inside the system, inside the control volume, and that includes mass or an energy. So if you add this condition, steady, it means nothing can change inside the control volume. Nothing can change inside the nozzle. Like nothing can change inside the duct. Nothing can change inside the heat exchanger. It means m dot in should balance m dot out. It means rho VA at the inlet, if the system has only one inlet and one outlet. If the system has multiple inlets and outlets, you have to take summation here, and summation of all the fluid in should balance summation of all the fluid out. But if it has only one inlet and outlet, then we have a rho B, you have m dot in being equal to m dot out. So rho VA is at the inlet is rho VA at the outlet. And if you add this condition that the fluid is incompressible, meaning density is constant. It means density is constant, so rho in is equal to rho out. These two cancel out, so we have V in A in is equal to V out A out. Right? V in A in is V out A out. And that's how, in a mass equation, which we call continuity equation, looks like for steady incompressible flow. Steady incompressible flow. And if, as I just mentioned, if CV or control volume has more than one inlet and outlet, then we need to take summation. Summation of m dot in is equal to summation of m dot out, or summation of rho v dot in is equal to summation of rho out v out. So that is for steady incompressible fluid. Incompressible means density is constant. And again, V dot is, volume flow rate. So if it's, a steady and incompressible, this is for a steady. For a steady, summation of all the, mass flow rate should balance summation of all the mass flow rate through outlets. This, you have to take the summation through all the inlet and take the summation through all the outlets. So all the fluid coming in has to leave. We substitute for m dot and write it in terms of density times volume flow rate, because m dot is density times volume flow rate. And if you add incompressible in addition to a steady, it means density is constant. So rho at the inlet is equal to rho at the outlet. Rho is constant, so you can cancel out rho. So summation of all the volume flow rate in balance summation of all the volume flow rate out. And volume flow rate is VA. So it's V in, A in is V out, A out, right? I'm going to stop here, and next time I'm going to pick it up from here. Next time we're going to meet in the class that's going to be next Monday, right? So if you have any question, I can stay after the class. Is there anyone who wants to see me after the class?
I have a question.
Yes, please. Your name?
Sarkis, but I mean like after the class, I would like to review one of the problems we did earlier. If
All
possible.
right. Yes. Okay. Yes, of course. Anyone
Professor?
else? Yeah.
Yes, I have a question. On Monday, are we gonna like kind of go over what what we might have on the exam and stuff?
On Monday, we may. Yeah.
Okay.
Monday, or maybe, I use Tuesday and we are Zoom session. So I'll let you know. Okay.
Okay. All right. Thank you.
Thank you.
Professor, could you help me review